Hello? This is the chill 10 minutes or so before the talk. Hello, hello. Does my audio sound acceptable? I'm trying to pull this off without putting my actual headset on. It's just sort of sitting in my lap. Crisp and clear. Nice, thank you, thank you. Good, good, good. Crispy like baguette, more like crispy like that focaccia I made yesterday. Oh, little dark on the bottom. First go though, not too bad. I've oh, cadre. Sometime I might take some pictures of what I did to my room for this setup. I've inverted my my desk so that I have better lighting. But it's quite the weird setup. Haha, Lord, nice, nice. Got the squad in the chat. Aw, Zach. It's so nice to see all these little names appearing in the chat, people that I know. It's wonderful, thank you. Yeah, I'm not worried. I think the typical UF astronomy faculty member is capable of making an account. If not, it's no big deal. Things can be made during the stream, or the actual conversation or defense with my committee won't be over this. We'll have an actual Zoom call. I'm just concerned about the number of people that may pile into this. Dissertation waiting room. That's been the past 3 years? 5 years? Dissertation waiting room. You are certainly welcome to. Yes. Always welcome to see that pointed and deep question at the end. Since we still have 3 minutes to go, the URL to my slides is on here. If you want, you can open them up, rifle through them, whatever, or follow along. Thank you. Thank you, Troutmans. You can go to this URL, right? So my slides are actually just a website because Reveal is amazing. So if you really want, you can probably even zoom in on them and whatever. And hit view source, grab my figures, whatever. How do you pronounce Safelin? It's the handle that I ended up sticking with for all things online, because I needed a handle for Lord of the Rings Online, right? And when you create a character, they present you with this pile of prefixes and suffixes, and it was tradition in the game to just mash them together. And this was also when I was in my second year or so of French, so I have this serious predisposition for any word that I don't know to assume that it has some sort of French-style pronunciation, as opposed to English. Yes, it does. Encourage or discourage throwing bits? I don't really care. Are we default muted? Yes. You can't talk with a voice. You can type. I didn't know how many people would show up. Currently we're at 41 viewers and 41 people attempting to talk. Yeah, that could get messy. Okay, so it is 11 o'clock. So I'm going to start. Thank you, Kadri. I do appreciate the pen. So since there's no one to actually give me an introduction, I'm going to introduce myself. I don't know if my entire committee is here. Okay. There's 2 members. Anthony Paul. Okay. Christina. Do we have quorum established? Yep, but is Anthony here? This is the question. Okay, perfect. So, yeah, that's fine. So by means of introduction, I think most of you know me personally, but what some of you may not know is that for the first 2 years that I was at UF, I studied exoplanets. And now I'm presenting a PhD dissertation talk on Lyman alpha blobs, something very far removed from planets. The backstory to this is that I spent 2 years working on exoplanets, really liked the science, but the problems that I found really motivating and the group interactions that I really liked were much more about programming, much more about getting research done when it was when we were almost running out of the compute resources with which to do it. And so at the end of my master's presentation, end of that project, I was sort of looking for a new sort of environment, and there was this new professor who just joined the department. He gave this really good job talk. I really liked his energy. And then I had this meeting with him. I sent him an email, said I'd like to work with you, and he pitched me 4 project ideas. I think Lyman alpha blobs was the second one. I don't remember what the third and fourth were because I had sort of tuned them out. What I remember from that is just that Deshika pitched me something. There are these things that are big, they're bright, and they're poorly understood, and that was basically all that I needed. So the whole reason that I'm working on this project is because Deshika pitched this to me and I found it fundamentally interesting. The title that I wish I was presenting is much more general. The way that this project worked, it was originally very focused on Lyman alpha blobs, which I'll get into a definition of soon. But I wish I had taken a different angle and doing this research from a broader perspective, studying massive galaxies, where Lyman alpha blobs could be some subset of this. We'll get into a little bit of exactly why this is. But this research is a somewhat extensive project, and it could not have been done without help from a lot of people, most notably Deshika, my advisor, who has been an invaluable resource, especially in terms of writing. The amount of hours that he spent helping me to assemble my thoughts into scientific writing has been extraordinary. Additionally, in terms of science and code input, Aaron Smith, who's currently a postdoc at MIT, contributed a large code base that essentially did the core of this project, which I modified a lot over the course of this project. I've touched nearly every line of code in it and done substantial improvements to it, but without Aaron's advice and without his contribution of code, this project would not have been done at the quality that it's been done and in the amount of time, certainly, that it's been done. He jumped me over many months of struggle with his code contribution. So this entire talk centers around Lyman alpha, so we need a pretty solid definition of Lyman alpha. So at the top of this slide, I have an energy level diagram showing the common transitions in hydrogen. And this is our Lyman alpha transition. So this is all the UV lines in the Lyman series, optical lines, and infrared lines. 122 nanometers puts us squarely in the UV, though. And part of the motivation of this talk is understanding something that's observed. UV is very hard to observe from the ground, but we're not actually observing UV. So I've already used a term that I hate, high redshift. So just to be clear, we're talking about redshift in this talk. Redshifts 2 to 5, which puts this 122 nanometers, redshifted by the expansion of the universe, squarely into the optical window. So it comes straight through the atmosphere. We can observe it. It looks like optical light, but if, as a careful observer, one looks at the spectrum, you can tell that it's Lyman alpha. What makes this line interesting, though, very interesting, at the bottom I have spectra from a classical numerical experiment for some optical depths. So we're looking at a source, and we've put a huge amount of neutral hydrogen between us and the source, and we see these outgoing spectra. In terms of increasing material, increasing tau optical depth from red down to yellow. And so what's really interesting about this is this doesn't look like an emission line. This looks like two emission lines. We get this double-peaked shape. This is entirely a radiative transfer effect. And these optical depths are massive. And the codes and the understanding that we're going to try to build up in this talk is expected to just cope with this. Because we're in a situation where there's a lot of Lyman alpha out there, and we want to make do with what we have. There are other regions of astronomy where they'll get to an optical depth of like 10 and say, ooh, this looks rocky, let's find a different line. Let's find some different way to approach this problem. But the fundamental problem with Lyman alpha is that there's a lot of it. We need to deal with these complex radiative transfer interactions. So we're just going to have to figure it out. The other last addendum is I've encountered one paper that found a double-peaked Lyman alpha line and did not, at least to my satisfaction, justify that they're not seeing this effect. They're not just seeing it's a normal Lyman alpha line, but you're looking through a lot of material, so you see two peaks. So it's an interesting caveat to this research that doesn't apply in a lot of astronomy. You see double peaks, usually you might conclude that it's an outflow or some sort of kinematics, but in this case, you really need to make sure it's not just radiative transfer effects. So that's Lyman alpha. Let's talk about Lyman alpha blobs. I'd really like a strong definition for this, but the closest definition that I have is basically what Deschker originally pitched to me. They're big, they're bright. By big, we typically in the literature one sees sizes like 100 kiloparsecs. This quote's in extent because a lot of metrics, especially for classification like this, are very fuzzy. People may not have the best resolution in their instrument, so they may be not so confident measuring an area, or they've got observations of something they're trying to pitch it as a blob. They're also quite luminous, but again, these values are typical, but there are a couple papers of Lyman alpha blobs, or these things that people say are Lyman alpha blobs at redshifts below 2, which don't quite meet those criteria. But I'm sticking with those for a general idea. And on the right is the first observations of what I would call is someone looking at a Lyman alpha blob and knowing what they're looking at. So this is a paper from 2000 to give you some idea of how recent this study is. There's a paper from 1999, but from reading that paper, and especially from reading the paper from 2000, this Steidl paper, it's clear that the authors in the Steidl paper knew that there was something weird. They also are the first paper, as far as I can tell, to call this a blob. They don't even put it in scare quotes. They just sort of drop the term, which is a fair warning to anyone doing astronomy. Be careful what you call things in a paper, especially if nobody's seen this sort of thing before. You might start a trend that confuses all the lay people whenever someone tries to explain to them what a Lyman alpha blob is. So I care about this project because I found it just intrinsically interesting. Deschker pitched me this idea. They're big, they're bright, they're mysterious. That was awesome. But there's actually a lot of other reason to be interested in Lyman alpha blobs, or Lyman alpha in general. So there's this open problem in astronomy as to how exactly the universe became reionized. So you've got this timeline of the universe, Big Bang, right? The universe starts out very hot, eventually condenses into a bunch of atomic material, but it's very opaque. Eventually we get formation of first stars. But through this whole era, the universe is essentially opaque because it's full of hydrogen, helium, and trace other elements that aren't ionized. So they interact very strongly with all the radiation. But eventually, when the first stars start to turn on, first galaxies form, they ionize their surrounding material, becomes transparent, and then we get this view into the universe. So when we look out into the night sky, we don't see this wall of neutral hydrogen outside of our galaxy. We can see other galaxies. So there's this transition phase in the universe. And there's sort of an open problem of exactly how that happened, what exactly drove it. Some people are pitching this reionization by the oligarchs. I love paper titles like this because you can just Google them and find the right paper. The case for massive UV bright star-forming galaxies with high escape fractions. So this is similar to Lyman alpha blob candidates. So the thinking here is if we understand Lyman alpha blobs, we may be able to constrain what caused reionization. So why do, there's other reasons though why one might care. Lyman alpha is probably ubiquitous in the universe. Nearly all the sky is covered by Lyman alpha. So says this one paper around high redshift galaxies. This is a result that we can nearly reproduce, but it requires a lot of compute. Basically, the case here in this Wysotsky paper is that the current observations of Lyman alpha tend to be constrained more by the pointing of telescopes and by the actual depth of our observations, and that if we peered long enough, we would actually see Lyman alpha everywhere, low intensity, but actually everywhere across the sky. Lyman alpha is also used to identify galaxy candidates at high redshift, higher than this work goes, but if we can understand the big bright things, the sort of easy targets, then we can extend this understanding to higher redshifts, to more distant objects, to fainter objects. So this is a paper from the beautifully named Silver Rush project. There's also one called Gold Rush, similarly picking their title very creatively so that it forms an acronym. So the central question of this work is, what powers these blobs? They're big, they're bright, we don't know why. So how did they get so big and so bright? We've got roughly 3 possibilities. So this first possibility on the left is gravitational cooling. The idea here is we've got this massive galaxy and it's pulling in material from the intergalactic medium, from the space around it. And just gas laws, this material's coming in, it gets compressed, it heats up, and then collisions within the gas excite electrons around the hydrogen atoms. They de-excite, they emit Lyman alpha, so we've converted thermal energy into Lyman alpha, which can then eventually escape. But to actually form this blob-like structure, there needs to be a lot of resonance scattering, or some significant amount of resonance scattering. Otherwise, we might just see these cooling flows. You might just see these sort of 3 spikes around most galaxies. The other possibility that's pushed around in the literature a lot is that this Lyman alpha tends to be driven by some sort of centralized source, whether it be very young stars or accretion around supermassive black holes. And that similarly, there would be Lyman alpha emission in smaller regions that needs to invoke resonance scattering to actually get out to a much larger space and cover this extended blob shape. The last case is a little bit interesting, because in this case we don't need to invoke resonance scattering so much. In these previous 2 cases, we have some sort of mechanism that's forming Lyman alpha, possibly in a much smaller space, and then scattering it out to a much larger spatial extent to get this 100 kiloparsec in extent object. But in this case, we will have an extended glob of hydrogen that is ionized from the outside, and the entire surface of it is glowing, possibly from the UV background, possibly from a nearby AGN, or possibly it might even be ionized from the inside, but ionized very thoroughly. So the plan in this project is to investigate all of these. And we're going to try to do this with algorithms. We're going to try to do this by building up a very sophisticated model. So the approximate workflow here is we're going to take these simulations from the Feedback in Realistic Environments project, these massive galaxy zoom-in simulations. So the idea of a zoom is you've done some sort of first principles oriented simulation of a large chunk of universe, but you found some galaxy that is really interesting for whatever reason. And then you'll take the particles that eventually become part of this galaxy, rewind them back in time, which is power that you get doing simulations that you cannot have doing observations, but we can know where these particles were in the past, interpolate on all of them, and then rerun the simulation. And then you get these, which is the simulations that we'll be working with, this very high resolution or much higher resolution galaxy embedded in a proper context. So we take these snapshots from their simulations, so periodically these simulations will save all of the state in the simulation to disk. We will convert these, the particle representation onto an octree. just to make it easier for us to do radiative transfer, we will run a Lyman continuum radiative transfer code across this to compute an ionization state. We'll get into why this matters so much a little bit later on. But for now, this is one of the parameters, the ionization state of this gas that is tricky to get correct on the fly. And then we'll run eventually a Lyman alpha radiative transfer code across this, and then we'll analyze the outgoing Monte Carlo radiative transfer photon packets. So this is the big computational expense on our end, but there's also been someone else who's invested a huge amount of compute up here as well, but we're just taking their outputs and running with them. So these are the galaxies that we'll be analyzing. This is, the top row is face-on, the bottom is edge-on views. This is the redshift of each of these, 1.7, slightly after the time window that we're looking at, and this is just their nomenclature for them. So these galaxies, though they're all massive, they range from this sort of nice spiral shape to this glob of stars and gas. So we're dealing with, in most of this work, with octrees. This bears a little bit of explanation. If you have a computer science background, these aren't wildly complicated. You can think of them as just a binary tree, but each node has 8 children instead of 2. And they're used to subdivide space. So at each refinement level, we subdivide each dimension by 2. And we can pick some refinement level. In a lot of, in some programming contexts, these are used to spatially organize points to make it fast with spatial searching. But for us, we're using this as a sort of adaptive grid, so that we can get this adaptive resolution, but also make it easy to look up what exactly the properties of the space that our photon packet is currently in. So we're going to run this ionizing radiative transfer. And this plot is just an argument that it matters. So on the x-axis, I'm going to show a lot of plots that look similar to this. On the x-axis is time in look-back time, so this is time in the past. And then z, the redshift, which is also time in funky units. And then the ionization fraction in this plot. So this is the total amount of gas that is ionized. So 0.5 would be half ionized, 1 would be totally ionized. So the simulation originally is this blue curve. And then we run our ionizing radiative transfer, and the simulation becomes significantly more ionized. Okay, so the ionizing radiative transfer mattered. That's encouraging. So now we need to do Monte Carlo radiative transfer, this Lyman alpha Monte Carlo radiative transfer. So we need to model emission, propagation, and scattering, and then eventually figure out something to do with it. So these are the only 2 equations in the talk, but they're sort of important because they point at a core complexity of this problem. So we have 2 mechanisms, 2 fundamental physical mechanisms, Lyman alpha luminosity due to recombinations and Lyman alpha luminosity due to collisional excitations. What's common in these equations is sort of uninteresting. So this h nu sub alpha, which is just the energy per photon, and then this integral. What's interesting is that we have these 2 coefficients due to recombinations that are both a function of temperature, times the product of the electron density and the ionized hydrogen density. Because recombinations are an interaction between an electron and an ionized hydrogen. Lyman alpha luminosity due to collisions is a function of the free electrons and the neutral hydrogen, the non-ionized hydrogen, times a different rate coefficient. So what's interesting is that all of these are in tension with each other. The temperature is plays a role in computing the ionization state, and the ionization state also feeds into the electron, the number of free electrons, because most of these simulations are so ionized that most of our free electrons actually come from ionized hydrogen. So this is complex interplay. We'd like to have the temperature and the ionization state correct, which is why we did that ionizing radiative transfer. So now looking at the model inputs for this, I can show you a snapshot. This is a density projection of the gas. This is a density projection of the stars. So in this snapshot, we have this nice little spiral structure here with this incoming glob of hydrogen. And we can see that there's a lot more stars in this sort of central galaxy. So we'll use these stars just to compute our ionization state. And we do that, and we get something that looks like this. So on the left is the neutral gas density, and on the right is the ionized gas density. So what's different between these is sort of unsurprising, but still interesting, that the dense gas tends to be neutral, the diffuse gas tends to be ionized. What's also interesting is that in this, we have this very diffuse, widely extended section of gas, which is probably shock-heated incoming accretion. What's also interesting is if you peer close to your monitor, you can actually see the octree grid far out in here, whereas it automatically refines when the density gets higher. So now using those ionization states, we can compute, and those temperatures, you can use those to compute the Lyman alpha emissivity. So there's no radiative transfer going on in here. This is just the emission. So we're not modeling any escape. So this is almost as if you had magical sort of X-ray vision to see through this simulation. And these, unsurprisingly, these are almost inverses of each other. This tends to favor the more distributed gas. This tends to favor the more compact gas. This is recombinations. This is collisions. But what's also very interesting in these plots is there are all these little knots in here. These are star-forming regions where there's a lot of ionization. So now, so that's emission, which is the simple part. The rest of this, I want to explain a little bit what makes this work so computationally intensive. The problem is random number generation, which at its core is a simple problem. Random number generators can be implemented with a couple lines, not even that many instructions. But the problem is that we don't just want any old random numbers. Random number generators are easy to build that generate numbers in the interval 0 to 1, all those decimal numbers, great floating point precision and everything. But we don't want random numbers on that distribution. We want random numbers on some physically relevant distribution. So the core of this works like we're going to sample some sort of distribution. We're going to do a small amount of physics, but then we'll need to sample another distribution. So we spend a huge amount of CPU cycles actually sampling distributions, and we need to do this cleverly. For simple problems, for example, picking a random direction, one can imagine doing this. You've got this interval 0 to 1, you can just scale it up to 2 pi or 360 degrees, and there you have your random angle. But for more complicated distributions, we need a little bit more rigor. So the general procedure for this is you have some probability distribution function. You compute an integral of that to get a probability a cumulative distribution function, which goes from 0 to 1, and there's our 0 to 1 mapping. We basically plug in our values from random number generator onto the y-axis and look them up on the x-axis. So what this means is to do this efficient random number generation, we need a function, we need all of our distributions to both have an integral that we can compute, and once we've integrated that, we need to be able to invert that function. This is a tall order. One of the interesting deceiving things that's done in a lot of math classes is you'll be presented with functions that you can integrate or that you can invert. But this is not something that we can do in general. In particular, there is a distribution that we encounter that looks like this, where we've got some Lyman alpha photon coming in, and we're looking at what the probability distribution of the gas velocities that it encounters are. So there's two lines in here that are being convolved together. There's this Gaussian distribution, which is centered on 0, and then we've got this Lorentzian peak, which is the line, the actual hydrogen line, and these are offset from each other. This is basically where things get really computationally intensive because we can't integrate this function, and inverting it is also going to go very poorly. So we use complicated numerical techniques to draw random numbers from this distribution. And from running Colt, I can say I have spent millions of CPU hours sampling this distribution, and just to get the Lyman alpha scattering correct. So this is a great simulation from Max Gronke, which gives you some intuition for what this Lyman alpha scattering looks like, which we're about to see some of. But the takeaway from this animation is that the Lyman alpha does a bunch of these scatterings, these little whitish portions, where it gets stuck at line center. it sees very high optical depth, and it does a bunch of random walks for very little distance, but then eventually it gets kicked out into the wings. It gets kicked out into these red-shifted or blue-shifted tails, and then it can jump very far. This is how we end up pushing Lyman alpha into this double-peaked spectrum. So this is what our simulation from before looks like. If you were paying attention to the scale on the color bar, you'll notice that this has shrank quite a bit. The amount of resolution that we get here is strongly dependent on the number of samples that we run. For all of the radiative transfer that we did for science purposes in here, we run 10 to the 7 Monte Carlo photon packets. So this is our Lyman alpha blob. That doesn't look a whole lot like a blob until we convolve it with a PSF of a typical telescope. So this is the resolution basically that we can generate in a simulation, which is very high. You convolve it down with a telescope. And for actual comparison with observations, the Matsuda papers are great for this because they often include pictures of their blobs. And so the scales here are a little different. Here's our 100 kiloparsecs, and here's my 100 kiloparsecs, right? So this blob here at 10 to the minus 18, which is what these contours are, does extend. Great. Okay, so we have output that looks about correct, but is it the right luminosity? So again, over time, we have the Lyman alpha luminosity with radiative transfer, so we've got all the escape properties in here. And then we have these 4 halos, and they all pass through roughly this distribution, these gray dots of what is observed in the literature. Okay, but our previous argument of area was a little bit low in rigor, so I'd like to do a little bit better than that. So now I've plotted for a number of surveys, the area that they quote for blobs as a function of their surface brightness, cutoff, their sensitivity. I've also plotted these curves, which I can render because I have simulations, and I can sort of do observations at whatever precision I want. So this axis may be backwards from what you're expecting, but notionally this is how much blob area you observe growing as your telescope gets better. This is sort of telescope precision increasing to the right. And we match up pretty well, especially at this sort of redshift 3 curve. There's a lot of observations that are done at redshift 3. And I have every other snapshot here. So this is Halo A1. It's got this nice evolution, starting from redshift about 4.5, evolving to the right and then down, reading as you would a page, down to redshift 2. Here we can see basically these cooling streams coming in. There's definitely some slightly different morphology going on down here. Halo A4. This was my sort of pet halo. Somewhat unfortunately, Deshiga encouraged me very early on to pick a pet halo or a pet snapshot, and I picked this one, which has some very nice properties, especially looking back. It's got this beautiful evolution over time, it's easy to understand, and then eventually I ran all the other ones. Yes, we will get to orientation in just a second. And then this is the halo that I was given when we'd almost thought that we were done. We had a video conference with one of the FIRE collaborators, and he pointed us to this other halo. This is the very high mass one. It is an absolute mess, but it's glorious, and we'll look at it in more detail in a little bit. So we can look at this from multiple angles, actually. For computational convenience, we can render from just one angle. But for visualization purposes, we can do our ray tracing along an arbitrary number of angles. The dark lanes, I don't have a great explanation for. They're not traced exactly by the neutral gas, if you plot the neutral gas density. But as you can see, as this rotates, it's essentially hydrogen gas that's in the line of sight. The complexity of Lyman alpha radiative transfer is that the gas both glows and absorbs and reflects. So depending on exactly what the morphology of the gas is that's along your line of sight, and also what it's backlit by, it will look different. So as this simulation rotates, the side that's closest to you is moving to the left, if that helps your brain get the rotation correct. You can see some of these dark globs will look dark, and then as they turn, they will look brighter because they're actually reflecting. This has an interesting sort of connection to biology. This is behaving almost like a mirror, but it's not actually a mirror. There's sort of an opacity gradient, a very sharp gradient. And so these Lyman alpha photons random walk down the gradient, almost as microbes will move down a food gradient, because they're just taking random walks, but along one direction the random walks are preferentially much longer. So now, remember the whole point of this project was to figure out what the source of Lyman alpha is. So I can plot up for each of my halos the Lyman alpha luminosity due to recombinations and due to collisions, with and without in the paler colors, just emitted, and then with the radiative transfer effects. And then we can see for all of these that they are dominated by Lyman alpha luminosity due to collisions. So that's it. That's the project done. Their Lyman alpha blobs are dominated by collisions. We've seen things that look like cooling streams. Project over. But there's one little addendum that I'd like to add before we conclude, which is that there's some interesting radiative transfer effects. In particular, I mentioned line of sight dependence, which is how I generated that video, but also all these outgoing Lyman alpha samples, right? I can redraw from the distribution. So I can either consider all of the samples going out, or I can pick just around one angle, and I can generate an escape fraction along a particular line of sight. So I plotted the median escape fraction in the darker color, and then sort of a gradient moving away from it, and showing the distribution of escape fractions that one can see with respect to line of sight. And there's maybe half an order of magnitude variation. But okay, so that's basically the project, right? Except, no. One of the interesting possibilities in this project is that AGN drive Lyman alpha luminosity. And in the simulations that we have, there's no AGN feedback. There are black hole particles that absorb gas, but they don't push energy back into the simulation. But remember, we did ionizing radiative transfer, so we can construct a clever lie. We can construct a clever lie wherein we simply tell our ionizing radiative transfer code that there are some really bright stars. Just a few, like maybe 2 or 3, and at particular locations. So we can use this ionizing radiative transfer code's belief about stars to put AGN back into this model. And when we do that, we see a very, very different story in terms of what dominates. See, we are now totally dominated by recombinations, almost, usually. We also see an interesting story now in terms of the escape fraction. So remember, since this is a log plot, the vertical distance between the pale and the solid lines is our escape fraction. And so these plots are a little bit noisy, but the escape fraction due to recombinations is very, very close to unity. The escape fraction due to collisions is much larger. But we see much higher escape fractions, right? So there's very much smaller effective Lyman alpha radiative transfer with the AGN on. We can also take a look at these. So this is the big glob messy simulation at redshift 2. And so now I've plotted the Lyman alpha luminosity and the escape fraction. And what's interesting is that on the right with the AGN on, the escape fraction is going nuts. It's changing very rapidly with respect to line of sight. This is an interesting observation. The images also look visually very different. So on the right, we can see a lot more of these sort of dots, bright patches, and on the left, we see the image much more, Lyman alpha much more distributed. And there's also some interesting structure going on in this glob up here, which is, it's mostly just visible up here, which is these almost spoke-like structures that form. This is essentially self-shielding. You can see these spoke-like structures much more often in simulations of, for example, supernova outflows, burning away gas or in photodissociation regions. And now, when we look at the variation of luminosity with respect to line of sight, it's much larger. We also see much higher escape fractions. In particular, in these two bottom halos, we can see 1 or maybe 2 orders of magnitude variation with respect to line of sight. So this poses somewhat of a problem for an observer. This means that if you're looking at a Lyman alpha blob, and if it has an AGN on, you have to be very uncertain about what the actual mechanism driving this is, about what its luminosity is, because what you're seeing could be very dependent on what the orientation happens to be with respect to the Earth. There's also, we see this massive variation, so I went through these simulations and picked out one simulation where the variation was particularly large, just to get some idea of what's going on here. Basically, this is we also see these escape fractions that exceed 1. Basically, this is because the simulation has a structure that's almost similar to a laser cavity, or a light bulb where someone has now put a mirror behind it, where there's structure that is sort of reflecting Lyman alpha back into the line of sight instead of letting it escape away. So we get this escape fraction that varies from less than 0.1 to more than 1, and this massive difference from turning on AGN. There's also this interesting observation about the visual difference. So we can quantify this using a metric from originally used mostly in economics called the Gini coefficient, which was originally a measure of income inequality, but we can use it to measure sort of luminosity inequality. For simulations with the AGN on, we get this one distribution of Gini coefficients, which are much closer to 1. With the AGN off, we get this very different distribution. So one can imagine drawing some sort of divider here and saying, to the right, it's probably got an AGN in it, and to the left, probably not. This might be very useful for an observer who sees a Lyman alpha blob and is wondering what this can tell them about star formation or about feedback. So we've addressed 2 mechanisms, but we never really talked about the UV background. Here is my one little experiment to demonstrate that it doesn't really matter. So we've taken our UV background multiplier, right, and we look at the Lyman alpha luminosity. And so at 10 to the 0, that's 1, right, which this is our reasonable guess at what the cosmological UV background is. And then we crank it up by 5 orders of magnitude, and we see essentially no variation. So there's these other mechanisms which can matter a lot, but we can sort of discard this from our consideration. So now we've got collisions and recombination depending on the presence of an AGN. So in conclusion, we've presented this first model that we're aware of that contains star formation, cooling, the UV background, and the presence of AGN all at high resolution, because this is based on zooms. This model can reproduce observations of Lyman alpha blobs, and we produce Lyman alpha blobs in all the halos that we model, which suggests that Lyman alpha is ubiquitous, but also the Lyman alpha blobs may be ubiquitous, may be a ubiquitous stage of massive galaxy evolution. These Lyman alpha blobs may be powered by emission from collisional excitations, and AGN have a dramatic impact on powering Lyman alpha blobs. Additionally, the escape fraction from Lyman alpha blobs is highly orientation dependent, even more so in the presence of AGN. That's the talk. Thank you. I would be quite happy to take questions from anyone who has them. And then once questions are exhausted, we will retire to a Zoom call. Thank you with the committee. So there is stream delay. Just FYI. So if your question isn't answered immediately. Okay. Explain again. Well, I didn't explain this at all. Okay. So the primary effect of the AGN is to produce way more ionizing UV when we do our UV our Lyman continuum radiative transfer. So we've taken, comparing these two equations, right? We've driven the ionization state way up. So this number goes way down, and this number goes way up. So we become much more dominated by recombinations as opposed to collisions. How do we know that we are not producing Lyman alpha blobs from more point-like sources? We know approximately because the Lyman alpha blob extents that we're seeing are larger than our telescope PSF. Significantly larger than the telescope PSF. So the telescope PSF is about this size. Right, and this Lyman alpha blob is many PSFs across. That's the hand-wavy explanation. Whether or not there's actually a large number of embedded point sources in here, that could entirely be the case. I'm not sure what you mean, Adam, by a negative escape fraction. Are you referring to an escape fraction? Oh, okay, greater than 1. Yes, okay. So because these simulations contain dust, if we had infinite optical depth, we would see no Lyman alpha. Right, so there's this, I sort of knew that I'd forget to mention this. There's dust in these simulations, which is how we get in all of these plots, a median escape fraction of less than 1. So, not entirely sure what you mean by a brightness limited surface. Is the large effect of AGN something that was generally expected, or is it a surprising result? It's sort of something that I expected. I expected to see some effect. Let's put it that way. Though it was unclear to me exactly how big it was going to be. There's a couple problems with the AGN prescription in here. One is that the AGN effect may be a little bit outsized because there's no actual interaction between the AGN and the gas other than to simply ionize it. So it's very possible that an AGN with proper feedback accounted for would have actually cleared gas out of this region very close to it where it's heavily ionizing. And so there may not be essentially this gas at higher redshift, which is just getting blasted by this enormous bright source and essentially fully ionized. Maybe more distributed, may have different morphology or something. How exactly we added AGN? So we have black hole particles, which are in the snapshot files, and then when we catalog all the star particles and we look up using stellar population synthesis what the UV intensity of them will be, and we plug those into a simulation code. We just add a couple lines to that input file, one for each AGN particle, and then we grab the mass of not the AGN particle, the black hole particle, and then we use, assuming an Eddington limited accretion with an efficiency of 0.1, which is about reasonable, we just compute an ionizing luminosity. We assume some AGN SED there's not an enormous dependence on exactly what we assume here. But we basically get out these very high ionizing numbers, and we just plug them into the simulation, right as if they're star particles emitting ionizing radiation. Right. Yeah, so I'm actually very interested in talking about this later with you, Adam. The answer is, to your question, is like approximately yes and no. The temperature of the Lyman alpha emitting gas is an interesting question because there's so much temperature variation across these simulations. So the gas that's distributed in this halo around here is close to 10 to the 6 or 10 to the 7 degrees. The dense gas that tends to emit in recombinations is 10 to the 4 or cooler. And the gas that tends to emit in terms of collisions is hotter than that. It's right around 10 to the 4 Kelvin. So I'm interested in talking about this later, though I'm not entirely sure how to answer your question. Have you seen my dissertation? That seems there is approximately a plot that's very close to that in there. It's not emission-weighted temperature, though yes, I agree that would make a very interesting map. Though in my dissertation, maybe if I can be able to pull this up, actually. Is this enlightening? Right, so in terms of what redshift this is at, everything that I've done is redshift 5 to redshift 2. What these objects are the likely progenitors of? All the galaxies that I've studied here have stellar masses greater than 10 to the 11 solar masses. So they're all massive galaxies. These are probably, in general, the progenitors of the large galaxies in the current time. The galaxies that either assemble or never assemble a disk might form the red and dead giant ellipticals. There's also another interesting open question in terms of what these things do, which is that there's a number of classifications of Lyman alpha objects. There's Lyman alpha blobs, which are the bright ones. There's also Lyman alpha halos and Lyman alpha emitters. These are all broadly Lyman alpha nebulae. They're fuzzy things in the sky that have some Lyman alpha luminosity associated with them. It's possible, and I suspect likely, that these are actually all the same category of things, that it tends to be that if you can observe Lyman alpha, and if you're looking at redshifts 2 to 5, or possibly even just greater than 2 or 3, everything is bright in Lyman alpha. That's just some sort of fundamental property about the availability of free hydrogen around these galaxies and the star formation rates in the universe. And so it could be that if you loosen your definition of Lyman alpha blob, that the things that form from Lyman alpha blobs is actually just galaxies, all galaxies. So what instruments would be useful for finding these? So what I would be interested in, oh goodness, did I break my stream? No, good. Phew. The most enlightening part of this talk is probably this, in terms of future missions, because this plot you can derive from the ground-based observations, but if we had James Webb observations, you get much crisper distributions here. These become almost totally separated. So if our AGN model is anywhere close to correct and you had James Webb observations, you could look at a Lyman alpha blob and be pretty sure, based on this, whether or not there's an AGN embedded in it. Whether or not AGN power Lyman alpha blobs is somewhat of an argument among observers because they see radio quiet and radio loud blobs. So. Thanks, Aaron. Are you referring to the luminosity versus temperature curves? This plot hides some deeper complexities in the actual data. This particular one, this particular graph is the simplest of all of them. They actually get more complicated than this. Oh. Brian Daniels asking the hard question. I don't know. I feel like I should know the answer to that question, but I don't know. Thank you, Zach. Are you going to look at other observables? There are other observables. So this project has focused on surface brightness images. There are spectra. We have spectra, of course, because right. Other lines. Other lines would be interesting. So one of the points that was made in this project somewhat early on was that let's see, something like these plots, you could almost derive something similar to this if we had H alpha observations or something like that. So if we had a model for lines like that, they could be very useful to maybe correlate something like Lyman alpha to an observation that gets you some measurement of gas density and see how these things line up. I don't have any personal plans to look into that sort of thing. Though that sounds like a really interesting project idea that could be very useful to people. wormholes. Oh, if only. Thanks. There's a lot of takeaways from this project. This project's been very valuable for learning all sorts of things about radiative transfer, about distributed computing, about HPC work. Right. In particular, the one takeaway from this project specifically that I did not expect to happen was that I came out of this. I went into this with sort of the sort of CS opinion that like global variables aren't great or whatever, but actually working with code where there is a universe state in the code and there's a lot of it, like Colt. I'm a big fan of this sort of way of organizing code. Would you like to cut off questions? Not just yet. So I've gotten some interesting lessons from working with other people, and especially you, on what patterns are useful for laying out code in astronomy. I also learned a whole lot about doing research and how complicated it gets and how hard it can be to plan these sorts of things. This isn't nothing ever works, but it's a variant of we never know how hard anything is going to be. This project laid out, initially Jessica did a great job of pitching me this project where everything was laid out. I just had to plug some code together and make it all run, and that took longer than I expected. But we got a lot out. I also have a huge amount of appreciation now for the level of subtlety that can come out of data. I wasn't prepared for the enormous amount of line of sight dependence in these objects. That took me sort of totally by surprise. And that's a sort of area of research that I think would be very valuable to have on these sorts of simulations. So, mirror effect with escape fractions. How exactly is the escape fraction defined here? So escape fraction is derived, in terms of calculation, it's derived exactly from the Monte Carlo photon packets. So when I have a photon packet, I know what its initial energy was and what its energy is when it actually exits the simulation domain. So I take all the photon packets that end up heading toward the line of sight, and I look at what their initial energy is and what their final energy is. And from that you can calculate an escape fraction. So that's the orientation-dependent escape fraction calculation. Coding language, there's 3, I guess. The code for the radiative transfer calculations is some mixture of C and C++, and then there is a small mountain of Python-based analysis scripts. Advice for an undergraduate aspiring to be like me. Try to learn outside of just what's in classes. I don't know if the time that I invested in learning more about programming has translated directly into PhD success, but it has certainly made me different than a lot of other PhD students. So I think there's some fraction of the viewers here, I would hope, are from communities that I've become involved in outside of astronomy. They're programming communities. And interacting with those people and just being around for their conversations has taught me a whole lot. Advice for future grad students who want to do this kind of work. Find someone who is in the field and can offer you very hands-on advice. So this work would have been very hard without Aaron. He got me set up and was able to give me sort of sanity check stuff and directions that I am Jessica might have been able to offer me advice, but I'm not sure if it would have been as detail-oriented as the stuff that Aaron was able to tell me. For grad students, probably the same as I offered for undergrads. Learn the supporting skills. This is something that everyone sort of knows is very valuable, but it can be hard to choose where exactly you're going to spend all of your time. There's only so many hours in the day, right? So I very deliberately deprioritized reading as many papers as most astronomy students do and prioritized working on coding side projects or reading tech blogs or watching conference talks. I don't know if I would suggest other grad students adopting the level of prioritization that I did, because I knew from relatively early on that I was not heading into academia, that I'm pursuing an industry job. But some prioritization on that level of either building up a coding hobby, so that can be your sort of mental relaxation activity, or thinking a little hard maybe about how many hours you spend reading papers versus splashing in a useful conference talk or something like that. What would you like the public to learn from your work? Coming into this project, I didn't have a good grasp on how unknown a lot of things in astronomy are, but how fuzzy so much of this stuff is. So in particular, this level of uncertainty, this is kind of typical in astronomy. Maybe not as large as this, but order of magnitude error bars in this regime are sort of typical, and yet we managed to build pretty solid conclusions. So when we quote exact numbers for things, sometimes these are carefully nailed down, or sometimes maybe someone building a press release has stripped the error bars off of our measurement. Though these are not error bars, right? This is a different sort of uncertainty. And yet we still have built strong certainty about dark energy and broad strokes, things like that. I don't know enough about the existing LAB surveys to comment on the ratio of radio quiet to radio loud labs. I know that I've seen that terminology in a couple papers. I don't know if the ratio is comparable to that of QSOs. There are probably enough Lyman alpha blobs known to make a reasonable estimate, but whether or not those all have radio observations, I don't know. I mean, certainly, right, from this, I've not really even, plumbed the full depths of the literature. I pulled maybe 80% of papers with Lyman alpha blob observations. I don't want to keep my committee here all day. So, yes, selection bias makes this a very difficult question. Especially if you notice that there are so many Lyman alpha blobs, mostly known right around redshift 3, because the Matsuda Subaru team is very good at conducting these surveys at a very particular redshift. So, I would like to halt questions in about a minute or two. Yeah. So if there are any closing questions, that's cool. Otherwise, in a minute, I'll turn off the stream. Thank you. Thank you. Thank you. Thanks. Thanks. Clapping wars in Twitch chat. Wonderful. Okay. Well, goodbye, everyone. See you in a little bit.